So as you can see today, the topic is Latent Dirichlet Allocation. That's what we're going to be talking about, Chris Shear and myself. I'm going to be referring to that as LDA from here on out because that's a bit of a mouthful. So the contents of the presentation is going to be that I'm going to give you guys a general introduction to the idea of LDA. And then Shia is going to take over and sort of go through a bit more of the nitty-gritty of the algorithms and the maths of how LDA works. And then Chris is going to give you a nice demonstration of the actual code and what it looks like after you are bored of listening to us talk. So what is LDA? So LDA is a generative statistical model that aims to determine topics and represent a document as a distribution of those topics. That's the definition, but what does that definition mean at all? So I'll break that down for you now. So essentially what LDA does is it, on its most basic level, is that it takes an input, it runs a statistical model, and it generates output. So if you come down with me to this diagram here, the input is documents and this letter K, which I'll go more into in a minute of what that actually is. It then runs the actual statistical model, which is the LDA, and then it outputs topics and distributions, which Chris, when he goes through the code, you'll get to actually see what that output looks like later on. And I am also going to go into what that output is, what that means. So first, I'm going to take you through the input. So what you need to input into the model is you need to provide it with multiple documents, which you might hear referred to as a corpus by Chris or Shia later on. It just means multiple documents, and this mysterious K. So what are they? So a document in this case, what is that? So LDA is referred to as a bag of words model. That essentially means that it views a document as a list of words, and it does not matter what order those words are in. So a document can be as simple as you can see here, cat, dog, burger, hot dog, or it could be as complex as a blog or a news article. But regardless of the complexity of the document, it simply just views it as a list of words, and it doesn't matter to LDA what order those words are in whatsoever. So that's what a document is in this case. And then what is meant by this mysterious K that I keep referring to? So K is simply just the number of topics you expect to find from your document. So let's say, for example, you expect your documents to be about science and cooking. This is 2 topics, so you would define K as 2. Now I'm going to give you a little description of the output before I go into the process. So topics and topic distributions is what LDA is trying to output for us. But what are those? So what is a topic in this case? So a topic is just a group of semantically similar words. So what does that mean? So if you look at our example document that I showed you guys earlier, you can quite easily organize the words in this document into 2 topic categories. So topic 1 could be cat, dog. Topic 2 could be burger, hot dog. Something you could note here while looking at this is that these topics aren't labeled. So it will just produce topic 1 contains the words cat, dog. Topic 2 contains the words burger, hot dog. Obviously, we could infer topic 1 might be about pets and topic 2 might be about food. But the LDA won't label that for you. It will just output topic 1, topic 2. And the reason it would output 2 topics in this case is because you defined it before you put the documents into the model as K was 2. So what's the topic distribution, our second piece of output? So a topic distribution is how much a document is made up of each topic. So if you look at the example document again, based on the topics we defined in the previous slide, you could very easily see that the topic distribution of this document would be 50% about topic 1 and 50% about topic 2. So that's the 2 things you're trying to get out of the model. So if we hop back to my definition slide with the nice little figure, you now sort of know more what we mean by documents and K that goes into the LDA, and you now sort of know what we're looking for to get out of that model. Now I'm going to give you a quick general overview of what the actual LDA does to turn that input into that output. So the LDA process. So keep in mind, you've put in multiple like a bunch of documents, and the LDA applies the process I'm about to talk about to each of those documents individually. So the example I'm talking about is applying it to one document, but it will then apply it to all of the documents that you fed into the model. So what is the process? Essentially, LDA tries to guess what the topics and the topic distributions could be. So it makes a guess at sticking a bunch of words into topic categories, and it makes a guess at how those topics would make up the document. So it might guess, like we did earlier, that cat and dog go into topic 1, and that the topic distribution might be 50-50. It will make a bunch of those guesses. What it does with those guesses is it uses those guessed parameters and the words from the original document to create a fake document. It will make a bunch of those guesses and a bunch of fake documents. And then what it does with those fake documents is it compares the fake documents to the original input document and sees if they match. And then if those two documents match, you know that the parameters it guessed are most likely correct because they managed to reproduce the document. That was a lot of words on one slide and a lot to take in. So I've now done a little visual of what it actually does, just to talk you guys through visually sort of what it's doing. So you input your document. It then will make a bunch of guesses about what the topics and topic distributions could be. It will then, using those guesses and the words from the original document, produce these fake documents, which you can see here on the right. It will then compare those fake documents to the input document. So you can see here that LDA guess 1, the fake document produced doesn't match the input document, so that's probably not correct. For LDA guess 2, the fake document again doesn't match the input document, so that's most likely not correct. And then for LDA guess 3, it does match the input document. So you would look at the guess you made there for the topics and topic distributions, because those are most likely correct. So that's how it goes through figuring out what the topic and topic distributions could be. So why do you give it multiple documents? Because I talked about how that example was with one document. Why do you have to give it a bunch of documents? So essentially, one document is not enough experience, if you will, to then create a model which, if you feed an unseen document into it, will be able to correctly predict the topics and topic distributions. So you give it a bunch of documents, and it does this process over and over again to create a really well-informed model, which it will then be able to use that model. If you then go, I want to know what this blog piece is about, you can feed it into the model. It will go, oh, well, I have a bunch of experience. I know that those words go into those topics, and therefore I'll be able to calculate the topic distributions for that unseen document. So that's essentially what it's doing. You're giving it a bunch of training and experience so that it can then correctly produce topics and topic distributions for unseen documents. What are those sort of two outputs look like? So your word to topic output is essentially, it's just saying apple, pear, grape is in topic 1, dog, tiger is in topic 2. And then when you feed it your corpus or your documents, it will be able to go, oh, I've read document 1. I know these words go into these topics, so I can determine that document 1 is 100% about topic 1. So that is essentially how you train the model and the sort of endpoint you're trying to get to, where you can then use that model to predict unknown topics and topic distributions of unseen documents. So that's the end of my section. I hope some of that made sense. I will now pass you over to Shia, who will share her slides. But thank you guys for listening to me. I hope that made any sense whatsoever to anyone. How do I? And now I'll let Shia take over.
Can everyone see my screen?
Yeah.
Yeah, okay. So yeah, now I will continue Louisa's presentation. Yeah, thanks for Louisa's introduction. It's very interesting introduction. And I'm sorry I talk about some boring math in this happy Friday afternoon. And yeah, so the LDA model is come up by David Bly, Andrew and Michelle Jordan in 2003. And to learn this model, we first need to understand what's the big ideas of LDA. So there are two big ideas. We have to learn it very clearly. The first is each document can be described by a distribution of topics. And the second one is each topic can be described by a distribution of words. So what does this mean? We can see the two triangles in this graph. So the bigger triangle represents the word simplex, which means the word space, and the small triangle means the topic simplex, which means the topic space. So for the real life problem, is the dimension usually are very high. So to make everyone understand more clear, we simplify it into a two-dimensional one. So as we can see, there are many points inside this small triangle. They represent documents. So each point represents the document is represented distribution of topics in each document. For example, this document point, like let's say 0.6, 0.25, 0.15 means the document. This document consists of 60% of topic 1, 25% of topic 2, and 15% of topic 3. And outside the bigger triangle, we can see the topic 1, topic 2, topic 3 are 3 points of the word space. And I just randomly set the word to be car, house, hamburger, and it could be any other words. So the topic 1 got a point. Let's set it to be 0.7, 0.2, 0.1, and we can see the topic 1 consists of 0.7 times car plus 0.2 times house plus 0.1 times hamburger. That's how this two assumption means. So each document is a distribution of topics, and each topic is a distribution of words. So we have a brief understanding towards our LDA. Sorry, this is our LDA space. So we have already talked about LDA space. Now we're gonna move to structure of LDA model. I know this seems a little bit scary yes, a little bit complicated, but I'm gonna use only very simple concepts to describe this structure. So alpha is a parameter for each document, and as we talked about before, document is a topic distribution, and eta is also a parameter for each topic. So the topic is the word distribution. So from alpha here is actually a Dirichlet distribution. So Dirichlet distribution is a distribution of distribution. We will talk about that later. So from alpha, we generate a distribution of distribution theta. So theta is a multinomial distribution. It represents a distribution of topics. And then we have already initial a distribution of topics. Then we use that to generate, to assign topics for each word, but it's just randomly assigned. We didn't know whether it's correct or not. And then we add this part into this model. We use eta to generate another distribution. This distribution is distribution of words. So let's say beta. So once we have beta, we have distribution of words. We have initial a distribution of words. We have initialize a distribution of topics. We will put them together and get a document of n words. So So as Louisa just talked about, we make many random guess about the document, but it's not correct at the beginning, and then we use some method for iterations and make the documents fix completely the same with the initial documents. That's the training idea of LDA. So let's simply talk about Dirichlet distribution. We use a three-dimensional example here, and as we can say in the graph, how does alpha affect the shape of theta? So large alpha values push the distribution to the middle of the triangle, like this paragraph. We take alpha to be 555. And smaller alpha values push the distribution to the corners. Let's look at here, alpha equals to 0.2, 0.2, 0.2. So Dirichlet distribution is just to initialize a distribution for our distribution of topic and distribution of word. That's why we apply this Dirichlet distribution. And another reason is Dirichlet distribution is a congruent distribution in Bayesian network. So of multinomial distribution. So it can make our computation more easily. Okay, so far I put this graph again, and what we know is we set an initial parameter alpha, we set an initial parameter eta, that's set by ourselves, and we have the input documents. That's what we have so far. And what we don't know is we want to use our initial value to generate the correct distribution of topics theta, and we want to use our initial parameter to generate our distribution of words beta. So, and also we want to know the topics. That's the key we want to know. We do this topic modeling. We just want to know the topics. So what we want to know is, in mathematically it looks very complicated, but I will try to explain it. So what we want to know is, given documents D, the input documents D, and our initial value alpha and our initial value initial parameters eta, we want to know the distribution of theta and our topics set and our distribution of words for each topic beta. But unluckily, this posterior probability is not tractable in computation. So it means we have to do some approximation methods to do that. So about Bayesian inference, there are many methods. The first one, gives sampling, are most commonly used in nowadays. And another popular method is variational inference. And also there are stochastic inference, expectation propagation. I'm not gonna extend this because it takes maybe a long time to explain the concept. But yeah, I've tried to write them into Scratch. This one could be would be the most easy one, I guess. Yeah.
Great job, Xia and Louisa. So what have we learned, just to summarize a bit? We are talking about something called a topic modeler, essentially trying to infer the possible topic, the possible ways you can break a bunch of documents for what we would call topics. There's some interesting things about this particular topic modeling. The first thing is that it considers a document. generally in classifications or similar things, you would try to get a single topic out of the document. The nice thing about this is that it breaks down a document into a distribution of topics. So it just doesn't go for one topic, it kind of infers the percentage of possible topics that could cover a given document. Then the name is Latent Dirichlet Allocation. So latent means, latent refers to the topics, essentially. Latent means is something that cannot be observed or measured. Like, for example, when we're looking at the document, we can measure the frequency of the words, but not the topic, really, unless you define it in some way that can be just gathered from the document. This is something we unobserved that we need to infer. So that's the topics that we're trying to infer. These are the latent variable. Dirichlet is because of the particular way that we are modeling topics and documents. Given the name of this fellow, Dirichlet is actually a very simple distribution. You know that if you take a coin is just heads or tails, right? And there's a probability of spinning a head, and the probability of spinning a tail is just 1 minus the probability of spinning a head. That's because we know in probability, the sum of the probabilities of the events must sum to 1. And the Dirichlet is just an extension of that. Instead of having a coin with 2 faces, we're talking about more than 1 face. And so the Dirichlet distribution essentially divides this probability into all the possible events so that their probabilities adapt to 1. So that's it. And allocation is because you're allocating that particular a particular weight, a particular probability to a topic. So I'm going to show you what it actually looks like. So I'm just present. Hopefully you can see this. Can you all see this? Yeah or nay?
Yeah.
Yes.
Yeah.
Yeah.
Are you still awake? Okay, so I'll make this a little large. For this particular example, I'm using a library called GenSim, which implements a particular version of the LDA. And what I've done is the following. I took a data set called the 2NG data set, which is basically 20 news groups. Someone bothered to go in a forum and extract 20 different news groups. So the examples are alt atheist, comp graphics, Windows miscellaneous. There's some about hardware, some about for sales, motorcycles, autos, baseball, hockey, electronics. And it's 20 of them. And they've just scraped some message posted in these groups. And cleaned it up for us. And so if you're curious about what it looks like, this data set is basically the group that the group we're considering, the news group, and then the message. And it's just a list of this. It's just a list of these pairs. News group, message. And so I thought, okay, so let's train an LDA with this data. So let's split this data set into one for training and one for testing to see how we're doing. And so the idea is we know that from the data set we have 20 topics, and we use these documents from the training sets to essentially see how the LDA divides this corpus into 20 topics. And so the first thing we do is we call, this is actually a file. So first of all, we call the LDA function, horrible name, but basically I'm turning this into an LDA model. Let's just show you the output. So actually, I didn't save. Let's just actually show you the code first. So this is the code right here. What are we doing? We are loading the corpus, and this part here just cleans it up and puts it in an array. So now we have a list of documents, and each document is basically a list of words, a list of tokens. Then, as Luisa mentioned, this is a bag of words model, which means the input to this thing is basically a set of words and a frequency for each word. And so this is what this part is doing, and you will see the output in a second. And then we just create the LD model. We pass it the corpus, and we tell. This is the important thing about this model. You tell it how many topics you ought to find, and the model will basically split the corpus into this number of categories. And then we just save the model so we can retrieve it and work with it. So let's try this again. So I stopped it because the model takes about a minute and I don't want to go ahead, but I just wanted to show you the output from this. So the initial line that you saw is just the dictionary. It showed you the each of the tokens that went into the dictionary. And what you see here is just what I was telling you about, the bag of words. So basically this is a list of lists, and each item in this list is the ID of a word in the document. So each document is being broken down. Each token in the document is turned into a numeric ID. And the second number is the frequency in that particular document of this particular word. Just as an illustration of what the kind of data structure we're working with here. So now we've created, just pretend this thing ran for a minute, and we created this model. So the second thing I want to do is just to show you what is done essentially. And so the show method, what it does, it just loads the model that we saved and just it shows topic. So this basically it will show us the 20 topics and the most relevant words that it thinks make up each topic. So let me show you what that looks like. There you go. So this is we see that it's a list of 20 items, one for each topic, and this is kind of what Shia was showing you. And this is basically a list of the words that he found across all the documents, the words that he thinks have most weight for this particular topic, topic 0. Another thing that both Shia and Luisa pointed out, these things are not labeled. This was just a topic 0, and topic 0 is now, so the idea is the assumption here is a document about something is likely to have, some particular words feature more than others, right? So something about football will feature words like, ball and goal more than others. And here what we're seeing is for topic 0, this is what the LDA thinks the most relevant words are, the words that have most weight. And we can see that's Palestinian, bike. So the fun thing for us now to have a look at is whether the words that have weight for a particular topic actually make sense. So let's see, topic 0, we have Palestinian, bike, therapy. I should mention these are stems. So do you know what a stem is? As opposed, so
Yeah.
You can basically stem words, but you're taking the root of the words, so you don't need to take into account of like plurals or verb like I don't know, hearts and hearts. the stem is hard, so you don't make, you just take the root, so you don't get confused with the extensions, and you reduce the number of tokens that you consider. So what else? Darren, shoulder, pregnancy, X-term. So this doesn't look very consistent. I don't think we can give it a topic ourselves. Let's see the second one. Radar, detector, that looks better. Mouse, captain, column, mask, color, cell, color map. That's a little bit more of consistency there. The one I saw earlier, let's see, for example, I mean, this one, I mean, these views are, you know, who knows what they post in there, but this one, for example, gun, moral, kill people, Muslim, Nazi, that kind, you could tell there's some consistency there. We would definitely give it a topic. Another good one, for example, is this one is weird. Will God love Russian? That's funny. This one is particularly good, I think. Space, NASA, launch, orbit. So I think it nailed this one. And mind you, I just ran it like for like less than a minute with just 10 passes. So this is nothing. You should run this for a lot longer and tweak the parameters. But just to show you what it looks like. Okay, so now we've got this LDA. It's learned from these models. Now let's see if we can predict anything. So let's keep this here because we need it. And let's instead run the prediction. So what is the prediction doing? The prediction is just loading the test set this time, just the way we did it before. We break it down into a bag of words again. We recall our models from disk, and then we pass it. We pass the model each of the documents from the test set, and we look at what we do is, so this gives us, you'll see in a moment, what we print is the document, then the real topic of the document, and then the estimated topic of the document. So let's have a look how it stands out. So let me just show you a small version of this. So just four documents we look at, so you can see the output. And then we try to have fun to see whether it gets it right. Oops. What did I do? Okay. Let's try this one. Okay, so what did I do? So the first thing I show is, given this document, as we said, a document, the LDA tells us, you know, the distribution of topics it thinks this document belongs to. So it doesn't give you one topic. It gives you the probability of each topic making up this document. And here we just return in the top 5 rather than listing the weight of all the topics. So we see this particular document. We should print the actual document so we can see it. But I have a dump from before, so for this particular document, which is from a topic, computational MS window miscellaneous, the top topics where topic 2, topic 5, topic 9, topic 16, and topic 17, we could see the top topic, you know, the one that we would pick if we really hard pressed to pick one topic would be in this case 2, because it looks like it has the most weight, the most probability of being the topic given that document. All right, so let me just see if I can recall my previous dump. Test response log. So this is the same, but just you can see the documents being the actual tokens that made up the document. So we can have a look at if this makes sense. So let's have a look at this one. I should point out that if you can look at the categories, some of them are really like, I mean, making a difference between PC hardware, Mac hardware, Windows X, and Windows miscellaneous. I mean, it's hard even for someone, you know, for a normal person. So some of them are really, there's really a lot of ambiguity. They all overlap heavily. Some of them same as politics miscellaneous, politics Mideast, you know, having seen just, we're talking about maybe 1,200 small messages posted on the forums. So this particular breakdown it's a difficult problem, and also for as few documents as these, and just running the LDA for a minute. But let's see. For example, this document, the original thing was, say, bibliography, program, post info, 2 months ago, don't remember, detailed software, organ literature, scientific public function. I mean, if we were reading this document, could we tell there was an MS Windows miscellaneous topic? Not really. But let's see, it tells us that the topic with most weight for gathered from this document was number 2. So let's see number 2 here. Remember, this is number 2 with the words that it found to have most weight when it comes to this topic. So let's see if there's something matching there. So here we have people, will, state, make, law, right? Well, not really. Let's find something with some, let's see what it thinks. So let's find something that it puts a lot of probability on. So let's say 0.7 to see if it gets any better. So we're still in hardware, but let's motorcycle. So even something, let's say motorcycle, the original document was octane, ethanol, corn, country, normal, Wilberg, people. I mean, I couldn't even tell if this was about motorcycles, really. Eat an animal. I mean, some of these things are weird. And so again, it thinks it's topic 2. And from here, you don't see much connection. Let's see if we're lucky here. This is just an illustration of what the output is and what it means and how you would go about it. Maybe matching the LDA unlabeled topics with real topics. Something is not, let's see this one. This is SciMed. Pick nose. Don't pick your nose. Equation, body, nose, loss, smell, harm. Yeah, this is about medicine. You could maybe say that. So topic 7, 78%. Topic 7 is this one. What do we have? Job, tax, insurance, money, pay. No, it's got it wrong, but you could see actually these words are very consistent. So that's probably something about money there. Let's find another one. What's this one? Space. Does it get space correctly at least? So things it's topic 9, comment, launch, date, familiar. This definitely looks like space, right? Wallop. It's a nice one. So topic 9, topic 9 is this one. Completely wrong, definitely. although this one is consistent.
I think this is a perfect example, though, of a case where, so the LDA hasn't had enough experience, if you will, going through and learning to be able to match all this up correctly. So to be fair to Chris's example, it's not that the LDA doesn't work. It's just obviously he didn't want to make you sit here for ages watching it learn.
But this is an illustration of how you go about these things.
Yeah.
And depends on the data set that you use, on the problem that you're using on. But yeah, it's fun to see how these things work out. I was going to point something out. Let me see. What else? Does it think about anything higher than that? I had something in mind I wanted to say and I forgot. It'll come back to me. Everybody's. Oops. So anything at 0.9. Let's see, where is it? Estimated topic. Bastard. Topic 12, let's see. Good back year thing, Isra. I don't know. Is there much? Can't tell. Yeah, the other thing also is you need to be careful because probably, because we didn't use many training documents, what's possible is that a lot of the words that are in the new documents were never seen by the LDA. So that's probably why you see this discrepancy. Whereas, if you pass it a lot of documents where you're likely to have seen the entire vocabulary, then it's easier for the LDA to work this out. Let's see, is there a last one? This is the only one at 0.9. All right, that concludes my illustration of this, essentially. So I hope you got a little bit about an overview of what this is, why you would do that, how it works, one possible library that you can use, and what that library gives you. What this library also gives you is the ability to update the LDA. So with all these documents now that I have in the test set, what I will, as I pass it to the LDA and do an estimate, I can also pass it to the update method. And so the LDA will add these new documents and relearn the parameters so that next time should fare better. There you go. So any questions, musings, ideas?
Yeah, it seemed like that what it had done and what you asked it to do was it kind of used the latent space, or it started off thinking of each word as a topic, but then actually built topics out of distributions of words to kind of what size you chose. It seems then that these are quite really clever, but abstract topics because they're just word distributions. So it seems like just looking at the most popular words in those distributions is maybe a bit of an unfair way of trying to judge how good they are. Because it might not be that a few of those individual words make up the distribution, but actually it's having a combination of them. And I don't know, maybe the reason it's picked them is more complex. It could be not that it's engineering or mathematics or something, but whether the topic is formal or informal, or again using a topic about Macs or Windows would maybe use different language. So they might actually be quite good topics. They might still have different images.
Yeah. I mean, one good point that you iterated that needs to be addressed about this particular thing is that these models tries to put a topic to each word. So to each word, it tries to assign, what topic, what probability this word pertains to a particular topic. And yeah, it goes to and as Shia has illustrated, it goes both ways. is about the relationship between topics and to each words, and how much each words contributes to a topic. But yeah, the example I used is, I could have used like a toy example to show you. You know, the typical thing where you have 50 documents with words like dogs, burgers, and houses. But we wanted to show you like what in reality what you faced again with this with these tools. And yeah, Shia is working on a particular harder version where we have to learn from real documents, and these are blog articles where we need to scrape this thing from scratch, and the ones we need to scrape, we have very, very big constraints about which ones we need for the particular problem that we're addressing. But yeah, as Shia has highlighted, we have we are in a somewhat fortunate position that TextRaiser is doing a good job at breaking text, assigning existing topics, labeled topics, I should say, to documents, to pieces of text. And we are trying to find out how can you bootstrap the LDA learning the parameters based on using TextRaisers as the ground truth. Because, I mean, objectively, we look at it and it does a good job of labeling the topic. So, using this I think is a clever strategy to, bootstrap our own model and also use it to label the topics that actually TextRaisers gives us a few things. Gives us the number of topics. So they already figure out what, the most relevant topics could be across the English language, given their training across billions of wiki articles and whatever else they trained it on, and also gives us it supplies us it's the oracle essentially for us. The oracle being in the learning space. The oracle is that thing you ask for the real the real truth about a query that you can use to update your own belief and posterior, as Shia called it. Also, I'd like to point out that this is not deep learning. So this approach is called probabilistic models. This is in the class of probabilistic models that are different from deep learning models, where deep learning models, the output of a deep learning model is, although they say it's a conditional probability of an output given an input, that's just an interpretation. What a deep learning model does is just creates an hypersurface and divides the input so that they can be split by this hypersurface. But then, in order to tell you, it doesn't tell you the value of where the point lands in this hyperspace, surface. It tells you whether it's on one side or on the other side. So to do this, it uses a non-linearity. So a 0 means that it's on one side of the hypersurface. A 1 means it's on the other side. And because they use a non-linearity that is continuous, they say, oh yeah, it's just like a probability. But that's not the case. Whereas what we're using, the approach that we're using is probabilistic. That means it's a Bayesian. It's based on the probability, the calculus of probability. It's based on prior, likelihood, and posterior. So it's a pure probabilistic. And the reason why we're doing this is because
I'll get a question in, Chris, because I've got a call any minute now. And you may have answered this. Unfortunately, I also had a call in the middle of the presentation, so I may be asking a question that you covered brilliantly. But you mentioned sometimes that you're assigning values to all words in the document. But in a language like English, I would suggest that half the words in the document have no meaning whatsoever, and they're there to support some kind of grammatical structure. Yeah, I'm thinking word determiners, for instance. Words like "a" and "the" are not very useful units of meaning. So, were you pre-processing the words to ones with, to some subset of the?
So I was.
That may be useful.
I made my life easier. So the data set I use was already pre-processed by, I don't remember where they were using that in a paper, and I should have referenced.
So part of that, I remember you introducing the set they used. So part of their pre-processing was to strip out.
Yeah. So exactly. So the basic processing we do is tokenizing. So first tokenize, then remove all the stop words. So, punctuation and the stuff like that. Then possibly lemmatize. Lemmatize means if you have a word, look in the lemma if you have a word related to it, but which is a canonical form of it. So basically you transform everything in a canonical form, and then stem. So take just the root of it. So you disregard if it's a verbal form or a plural, just discard that. You already have that token covered by the stem. So that's the typical stuff we would do to pre-process and remove all those words. Because you're right. I mean, if we just if we include all the words, then the would have the most probable thing of happening in every single topic. So it'd be useless. Yeah.
Great, thanks. Does it follow, just as an interesting philosophical thing, is it easier to do this in Chinese, given that the language has got significantly fewer pointless words? Sure. And might be more interpretive. Do you have any thoughts, Shia, on that?
So I've tried to do NLP project in Chinese before, and we have a stop verb, and we have a standard process for processing Chinese language. Is that your question? Sorry.
Well, just that it would strike me that in an iconographic or pictographic set of symbols, there's an awful lot less punctuation. So, so more of the symbols are meaningful and interesting and relevant. The sort of cleaning up you'd need to do would be different to the cleaning you need to do in English. For instance, most Chinese words don't let me tell you about your own language, but as far as I understand it through my study of Japanese, is that your written language wouldn't necessarily have any tense information involved. The pictograms are far more descriptive, and so the interpreter of the language is bringing more to it when reading it.
Yes. So yeah, in Chinese language processing project, there are someone who manually put the, there are some dictionary kind of things. They put every meaningful word. No, they put every meaningless word in a dictionary. So when we process like Chinese, I believe there also a kind of same thing in Japanese. So they put meaningless words in this dictionary, and when they're processing their data, they just use this like English stop words, English stop list. Then they just but this dictionary are usually manually made. Like many people choose the word and put it into the dictionary. We have some data in the public source like that.
Right. Interesting.
Yeah.
I'm going to have to jump on my other call. Thanks, everybody.
Bye, Dan.
Thanks everyone.